We stopped at KMT, kinetic molecular theory. I don't know if we got into it this time. Which one should I be highlighting here?
Kinetic molecular theory.
The second one?
Nope.
This one?
Yes.
The first one?
Yeah.
The whole thing?
No,
No,
just
just
kinetic molecular.
The bottom.
Last 3 words.
Oh, okay. Okay, so we talked about some properties of gases yesterday. The KMT, or kinetic molecular theory, explains why those properties happen. There's lots of space. The molecules of gases have a very tiny amount of mass, and they are moving very fast, and they bump into you. So much like a truck bumps into a car, sometimes there's a transfer of energy in you, and there's a force exerted. And so that is what's happening to your, to everything that the gases bump into. And since the world is filled with atmosphere, this is happening, on your body alone, like trillions of times a second. So those particles, when they bump into stuff, they exert pressure, and that's what you feel. That's what we call air pressure, or any pressure. That's how it's defined. So the pressure inside this container, or the pressure inside this container, okay, it's just a result of the molecules of air or whatever gas is in here bumping into the water surface and the inside of the container. And then that happens all the time, and so that's what pressure is. What other one am I highlighting?
The last one on there.
This one?
Yeah.
Yeah, whatever. That works.
Why is this one also the same thing?
I don't know, we should just be done.
Same thing on yours?
Yeah.
It's written twice?
Yeah.
You're not even taking notes, so I don't really care. But that's good, you said we should be done.
I'm taking.
If we were done, then how would you copy
Are
your
we
notes
done?
on it for the next hour?
I'm not copying anything, and I had this $4. It's notes from yesterday.
I'm not listening to you.
God.
I know.
Oh, we're done.
It's just easier if I stop listening to you. Anyway, that's what the kinetic molecular theory says. That's sort of attached to yesterday.
kidding? We're done?
I was just straight homework, you guys.
Oh.
We can measure properties of gases by, looking at them, investigating them. There are kind of 4 or 5 things that we're going to constantly refer back to. And so that's pressure, which is the pressure exerted by the gas. The variable is a capital P. Volume is the total volume occupied by the gas. Temperature is temperature in kelvins, which I think is already written for you, but highlight because it's not going to be Celsius this chapter. And then N is number of moles of gas. We won't get to that one until Friday. The first 3, though, are the ones we're going to spend a lot of time with today. Who said that? Question. Oh, you said under pressure.
Yeah, the
Oh,
song
okay,
Under
sorry.
Pressure.
Yeah, I think so. I've got a question, which is why I'm old. Okay, so pressure volume relationships. You're going to learn 3 equations today, and so you can think about. You're also going to learn the qualitative relationship as well. So the qualitative relationship you saw yesterday. As I decrease the pressure inside the container of the vacuum chamber, what happened to the side of the balloon?
Kind of went up.
It went up, and so it's an inverse relationship. As volume decreases, pressure will increase, or vice versa.
If my head was in there, would it grow?
Yes.
Would that be painful? Like really painful?
That is what they call the bends when you are diving.
Oh, that's right.
You have a certain amount of gas dissolved in your blood, usually nitrogen. And so when you're deep sea diving, there's a lot of pressure of the water sitting on top of you, and so that gas becomes smaller. And then the gas decreases in volume. And then as you come up, you have to make stops. And so I don't know what the actual number is, but let's say every 25 meters that you go up, you have to wait like 15 minutes or 10 minutes or something like that, like just sitting there. So that gas will expand slowly. If you come up super fast, let's say you're down 100 meters, and you don't blow up, but
Your blood starts foaming, right?
yeah, the bubbles in your blood become bigger, which I would understand is a very painful process. A lot of pressure all of a sudden inside everywhere in your body, and so then if that happens, you have to go into a decompression chamber for a certain amount of time. It's not very pleasant. And yeah, you can die sometimes. I don't know how that works, but you can. Okay, so I'm not super concerned you learn the names, but here they are. Boyle's law is the pressure-volume relationship. And since it's an inverse relationship, I think that if you are in math, and I think at this point in your high school career, you recognize this relationship as an inverse one. As pressure goes up, I notice that the volume will decrease. We got the volume in liters there on the left-hand side of the y-axis. On the x-axis, we got pressure in kilopascals. And I say, what is that graph is sort of indicative of a inverse relationship. One variable goes up, the other variable goes down. There's a, there's a couple things you should know about the inverse relationship. One is the equation, which I think hopefully there's enough space for you to write down there. Well, let's just I think there's a couple of like sort of key. These little pictures I learned in high school, which I think they're always fun to kind of relate these things to you. And so here's the one for pressure and volume. The pictures are they're just a way to sort of to kind of make sure that you understand the relationship. And so if you write PV together, as pressure goes down, volume goes up. That's just a little convenient way to remember that.
That's
You like
cute.
it? It's cute, right? Way too easy some of the other ones.
What is it?
This is the worst one.
That's the worst one.
But that also means the opposite, so as volume goes down, pressure would go up as well. Just make sure that you understand that, that's the relationship, but just so you can kind of remember things. The actual mathematical equation for that, if I gave you some information, would be this. Pressure 1 and volume 1 equals pressure 2 and volume 2. This is a classic inverse relationship equation. This you'll need to kind of sort of commit to memory. And so, you should write that down.
I love it.
You have a space there, cool. And you can do problems with that, which we're going to spend a ton of time doing over the next 2 or 3 days. And here's one of them. A given sample of gas occupies 523 milliliters at 1 atm. The pressure is increased to 1.97 atm. Temperature remains the same. What's the new volume of the gas? In these problems, you might see this. There's a variable here that's not written, and that's temperature. Temperature has to remain constant for this to work. And so in a problem, you might say temperature remains the same or temperature is held constant. That's the only way that this equation works, if you keep temperature constant, and number of moles temperature too.
Can't you just set up one explosion?
This is essentially the same thing, yes.
Gotcha.
Yes. The other one will be an actual proportion, but this one you plug numbers in, and then you just solve for the missing one. Yeah. So in this one, it doesn't matter what volume you're using. Here it's milliliters. It could be liters as well. But as long as they are, like if this first volume is milliliters, then the second volume should be milliliters. They need to match. You can't just take, liters and milliliters and plug them both in and expect it to work. They have to. The units have to match up here. So. I don't care, it doesn't really technically matter what you call this in terms of variables, but if you are starting out and you don't know what goes where, it's sometimes nice to say, oh, here's my first volume, here's my first pressure, and I want to know, oh, here's my second pressure right here, and I'm solving for second volume. It says what's the new volume, so. But if you switch those numbers, it would still work. If you called this V2, P2, and that P1, it doesn't matter what you call it. But there's going to be a lot of numbers in these problems, especially starting on tomorrow. So it's kind of nice to say, to sort of get a roadmap and say, oh, here's my first volume, here's my first pressure, especially tomorrow. Just keep that in mind. So this is the equation you use Boyle's law. Plug it in, you have 523 milliliters for your volume. You have,
Times 1.97.
oh, no, the old pressure is 1. So 1 at atm. And then you want to set that equal to, your new pressure is 1.97 atm. And then, ATM, and you want to solve that for your second volume. Okay. So you're essentially just dividing each side by what?
1.97.
Yeah, if you want to get V2 by itself, you divide each other 1.97. So 1.97 here. I'll just write this out really quick so there's no confusion. And then that cancels out. You get 523 over 1.97. The answer is what?
265.48.
265.48. And that would be milliliters, since the old one is milliliters, and that is what your V2 is equal to. Now, a couple of things. You can always come back and check and say, does this answer make sense? Well, what happened to the pressure in this problem? Did it go up or did it go down? And it went up. And our volume, when we solved for it, went down, right? It was 523, now it's 2.58, or I'm sorry, 265.48. And if you remember this relationship, you'd say, yeah, this makes sense. If I increase the pressure, the volume should go down. And that's what happened here. And so you can kind of do a self-check on these, which I think is kind of nice. You can also, if you want, I wouldn't have done this when I was your age, but now it's sort of what I do. You can rearrange this first before you plug things in. I'll do that sometimes now, but in high school I was like a total algebra idiot. So if you want to solve for V2, you can just divide it to a P2, you can have P1 V1 over P2 equals V2. And now you have a really convenient way to just kind of plug things in and solve immediately instead of putting the numbers in first, but some people don't like to do that, and I don't care which way you do it. whatever way makes sense for you. This is a a la carte learning system. Doesn't make any sense. Okay, next one. Temp and volume. Good to go, Chaos?
No,
Okay.
you said 45.
Help me go. Emotionally unstable.
I'm sorry, I yelled.
You would probably remember from yesterday heating and gas and cooling gas. We saw the balloon with the boiling gas on it, and I cooled it down. The balloon with the boiling gas expanded, and so heating and gas makes it expand. Cooling it makes it not expand, or sometimes called contracting. If you've ever seen a hot air balloon, that's how hot air balloons work. When you heat the gas in the balloon, it expands. It also becomes less dense when it expands, and so that's why hot air balloons float. And then if you let it cool down, it condenses a little bit, not to a liquid, but it condenses, it reduces its size, it becomes more dense, and then sinks on the bottom. Again, this is the important one for Kelvin, okay? If you don't remember Kelvin, you have to add 273 Celsius to get Kelvin. So if something is, let's say, 25 degrees Celsius, it's going to be 298 Kelvin. For these problems, you have to use Kelvin, so it's a little extra step for you, but this is a direct relationship. So heating and gas makes it expand, and cooling makes it contract. Charles was the person that did this, so that's called Charles's law. And basically the relationship is the temperature increases, so does volume. And a direct relationship graph looks a lot like this. As one variable goes up, the other variable goes up. Now, I know this is going to be a dumb question because you guys are really young and you do cool stuff, and you know, a loser like I am, you didn't grow up in the 80s. But there was this show called Charles in Charge, starring Scott Baio, and it was awesome. The shows in the 80s, I don't know if you don't really see them too much on TV anymore, because the 80s were a different time, and the shows were like really weird and stupid, and like campy and stupid and weird. And so this is the intro to Charles in Charge, which has like kind of a memorable theme song, which you might recognize from Family Guy. This is why I hate, not hate, but when you talk about Family Guy, I don't understand how you get like 90% of the jokes, because this is a joke from Family Guy where that guy was stabbing George Harrison, and then Peter was watching George Harrison. He was singing this song, which I hope works on this computer. I haven't really tried it. Please work. Please go. Oh, come on, don't do this. Hold on.
Just put it back.
I'm going to. Let's just let
Are you
it
recording
think for a
this, Caleb?
second. The song is much more catchy than that. Promise. Ready?
That's brutal.
At the end, I'll find it for you. So, I don't know why this doesn't work.
Failure.
It's a failure, but it's not my first, and it won't be my last. So I'm not really concerned about it. Anyway, Charles in Charge, here's how that relates to what I'm saying. This is Charles' law. And so it involves temperature and volume, and here's what you need to know about it. Did you hear that? How come that worked? Okay. The equation is it's a direct relationship. The direct relationships you divide. So you have temperature 1. No, switch that. V1 over T1 equals V2 over T2. This equation you can feel free to solve with everyone's favorite useful little mathematical,
Cross multiply.
whatever you call it, cross multiply and
I
divide.
love crossing.
I still tried to do it that last one, but it didn't work.
Yeah, you can't do it that one, but you can do it this one, obviously, because it's sort of set up. Now, the relationship, it's a direct relationship. Here's where Charles in Charge comes in. Television. Again, you don't remember the 80s, but it's a long time ago. And now, the antennas that you have for TVs, they don't
Oh God.
catch the signals, but see, it's like a TV with antennas. Charles in Charge was on TV. As one variable goes up, the other one variable goes up. Just take a second to wrap your head around how beautiful this analogy is.
Where did you
I don't get it.
I don't remember. So okay, it's called Charles' Law. I just tried to show you the show Charles in Charge. So it's on television, obviously. But as one variable goes up, the other one goes up as well. So it's like a TV with the antennas pointing up because one goes up. Which also means as one goes down, the other one goes down. So just don't forget that. People tend to mess that up. So there's the equation. The problem, again, you can solve with cross multiplication and division. It doesn't matter what these are, as long as they match again. But these you have to convert to Kelvin. They won't work in Celsius. Okay? You're going to add 273 to them. So when you read this, you say, oh, here's, obviously you read them. But when you're looking at it, okay, here's a first volume, so V1, here's my first temperature, T1, here's my second temperature, T2, and I'm sort of labeling things, at least in my head, as I'm doing that. So you have this balloon, it's inflated to a certain volume at 27 degrees Celsius. You put it in a dry ice bath, which cools it down to negative 78.5. Once it's volume, assuming the pressure remains constant. So you're keeping pressure constant. Don't freak out if you see that word in there, it's not a huge deal. You have to add 273 to these, so your T1 equals 27 plus 273. It's going to be 300 Kelvin. And your T2 equals negative 78.5 plus 273. What's that? Thanks. It's 194.5 Kelvin. Now you're ready to plug those in. They have to be in Kelvin. So 665 is your first volume. Your first temperature is 300. And you're decreasing the temperature, so your next temperature is 194.5 Kelvin, and you are looking for V2. Now, you'll expect this number to go up or down. You expect your V2 to be higher than or lower than 665?
Lower.
Should be lower because your temperature went down if you look at them, right? The temperature was essentially cut by a third, and so you would expect your number for 665 to be to decrease that much as well. Yep. Do the same thing. So you can solve this with cross multiply and divide. You take 194.5 times 665 divided by 300. What do you get?
431.
No,
434.
you're absolutely wrong.
431 point what?
114.
Good try.
Which is refreshing because Max has never been wrong. It's always nice when that kind of person is the person who yells, "You're wrong." It's always great. Which is why I know everyone in here loves Max.
How'd you get
Okay,
T1?
street somewhere.
See what I'm doing there?
Just tearing.
Turn it around. Alright, so this number is essentially 1/3 of what it was, and again, it matches up, okay, the information matches up, yeah.
Couldn't you solve it first and then convert?
No, because when you multiply, the numbers will be the same. It's like you're
Oh,
dividing by
then-
26 or whatever it was, 27 and same, so that would be the same.
That's when we were solving third. Never mind.
You have to, yeah, it's very important, that's a good question, you cannot start with Celsius and then convert to Kelvin at the end, it won't work.
Where'd you get the 273?
I had to add, when you convert these to Kelvin, so Kelvin equals 273 plus whatever your Celsius temperature is. And since these were given to us in Celsius, you're going to be converting to Kelvin a lot, so make sure you memorize that number.
I hate Calvin.
I know, me too.
Calvin here.
Last one.
Maybe it's enough for quiz. More?
Last one. What time is it?
Congratulations.
It's almost done.
I don't know, but you're being kind of mean, so can I go back?
Yeah, go ahead.
Look at known as gay.
Whoa, as
Okay,
soon as the
wow.
game is sec law, and let's all talk about it.
Let's all focus now.
No, it's like a freshman class. all of a sudden.
Okay,
It's crazy.
okay, I get it.
Yeah, I get it. You're a freshman. Anyway, so
I'm a junior, thank you.
I know you're acting like a freshman. See what's the funny part. Anyway, you know temperature and pressure. There's a relationship there. As you increase temperature, the molecules move faster. If they move faster, they bump into things with more force, and they bump into things more often. And so the pressure is going to go up as a result. And so temperature and pressure, those two variables there, they're directly related. As temperature increases, pressure will also increase. Keeping volume constant here, but that's okay. So Lewis-Tax law states that the pressure of a gas at a constant volume is directly proportional to the absolute temperature of the gas. So as temperature goes up, pressure goes up. Or vice versa. So the graph looks like this because it's a direct relationship. And I guess I should show you what those relationships are, right?
Yep.
I don't know.
Since it's a direct relationship, what would you expect the equation to look like based on our last equation?
Same thing.
Well, not the same.
Similar, but a little bit
Similar.
mixture.
Just with KPA instead of
I don't know what you're saying. The first, the last direct relationship, oh yeah, it was the one previously. Yes, you're right. So we have temperature and volume, and so I'll start over here. Temperature, 1.
Volume.
I'm sorry, we're talking about temperature and pressure, aren't we?
You're the teacher.
Yeah.
Yeah,
I don't know.
I don't know either.
T1 over P1.
By the way, P1 over T1 equals P2 over T2. Direct relationship, T is still on the bottom, but now we have P on top instead of V. And the picture, in case you care about it, since there's a direct relationship, draw the pressure and temperature, you can draw the P and the T both pointing down, because as pressure goes down, temperature will also go down and vice versa. Thanks, buddy.
Good shit.
Sub it in.
That was solid.
Good shift change.
I think your only good one was the TV one. I like
The
that.
TV one's really good. It's gonna be a lot better when I find the video for it to show you.
This one sucks.
I promise. I love. Never mind.
I live.
Well, I just think it's funny that you're like, 17 or 18 or 12 or whatever you guys are, and it's just like you've seen so much in your lives. It's like, this sucks. I'm so jaded. Whatever.
Jaded?
And I was like,
What?
come on, you've seen nothing. This is like, oh, summer's so boring. God, kill me. It's like,
Jaded.
It's boring.
and it's really funny. I think it's funny when you're jaded. I just don't find that really comical. I don't know why.
What's the definition of
I love
jaded?
that you say
The
jaded.
definition of jaded is like you've seen a lot in your days, and so like you're like extremely sarcastic, or like nothing impresses you because you're just like, whatever, I've seen it all, I've done it all, I'm 16, I'm the king.
Were you expecting temperature and pressure to just
Why would
blow us out of the water?
No, I know, it's just funny, I don't know. I'm not expecting it to like blow your mind or anything, I just think it's funny. Okay, last one. This frog is so awesome. I'm looking for a reaction somewhere in between those two extremes. Okay, we've got an aerosol can. You probably know what happens to it if you toss it into a fire.
Blows up.
It will explode. And the reason is because as temperature increases, so does the pressure, and eventually it's too much pressure for the can to contain, so the can will explode. Now, when you're reading this, you've got here's your first pressure. And again, label these because tomorrow you're going to have all 3 variables in one spot. And you're going to see 5 numbers in a problem instead of
Plus
3.
273, right?
You're going to add 273 here. So here's your first temperature and your second temperature. And when you do this, I like to just add the 273 off in the margin. So 22 plus 273 is 295. And that is your first temperature. I'm sorry, T1, I should say. And then 55 plus 273 is 328 Kelvin. And there's your T2.
Cross multiply
Now you
divide.
can, yeah, cross multiply and divide. Your first pressure is 101. Your first temp is 295.
What?
What did you do?
Nothing.
You're looking for the new pressure, and your new temperature is going to be 328. So if your temperature goes up, what do you expect to happen to the pressure?
Go up.
It's going to increase as well. So
Yep.
you cross multiply and divide 301 times 328, or sorry, 101 times 328 divided by 295. So your new pressure is what?
112.3.
That's it.
And that is going to be, since this was in kPa, your new pressure is going to be in kPa. Does it make sense? Yeah, temperature went up a little bit, so pressure will go up a little bit as well.
Doesn't.
That was really interesting.
We're not getting into the relationship here, but if temperature, and I kind of mentioned this last problem, if the temperature goes up by, let's just say it's, I don't know, something simple like 50%, or let's say the temperature doubles, okay, then the pressure will also double. So you can keep that in mind. So the ratio is that this went up by a certain percentage, so this will go up by a certain percentage as well. Say it's a direct relationship in that way. So temperature doubles, you expect the pressure to double also. So those are 3 of the main gas salts. We'll learn a couple more later.
What did you just say?
Avocados.
That's on Friday. Gas salts.
Avocados.
Avocado.
Can I use the restroom now, please?
Absolutely. Please take a long
Doing
time.
another problem.
Here's the homework problem.
I'm so jaded right now. I'm so jaded.